In this video, I will explain what enzymes are and what they do, along with other background information, outline an experiment that can be done under a lab environment, and give a real-world connection between the enzymes and how they affect our day-to-day lives. An enzyme is a macromolecule that acts as a catalyst, a chemical agent that speeds up a reaction without being consumed by the reaction. This is because reactions, although they will happen at a certain point in time, may take a really long time to occur. An example of this is if you add a cube of sugar into a cup of water at room temperature and simply stare at it waiting for something to happen. You could be waiting for hours until something happens. But if you start stirring, you could expect the reaction to take up only around 10 minutes. If it is hot water instead of cold water, then the time for the sugar to dissolve may only be 3 minutes. The reason for this is due to the required amount of activation energy for the reactants to shift into the transition state. In the transition state, there is enough energy for old bonds to break and for new ones to form. How do enzymes speed up reactions then? Instead of increasing the amount of energy available, enzymes are catalysts that lower the activation energy barrier so that reactions can occur even at normal temperatures. The active site where enzymes take in the substrate or the reactants are very specific to the reactant, kind of like a lock and key mechanism. But an enzyme is a very dynamic lock and key that is moving around, and once it makes contact with the substrate, this moving, also called induced fit, helps it fit snugly and securely around the substrate, after which there are multiple things that the enzyme does in order to catalyze the process, including orienting multiple reactants in a way better suited for the reaction to take place, stretching and bending the substrates to position closer to their transition states, providing a microenvironment for the reactant, say for example a more suited pH level, and even involvement of amino acids to make the reaction easier to occur. The enzyme lactase will be observed in this experiment. However, in order to observe the reaction rates, either the substrate, lactose, or the products, glucose and galactose, must be able to absorb light from the ultraviolet to visual spectrum for lactose to be used as a suitable reagent via spectrophotometry, which is not the case. Thus, the substitute orthonitrophenol beta-D galactopyranoside, ONPG, will be used due to the fact that it can also be hydrolyzed by lactase, and one of the products, orthonitrophenol, is able to absorb 450 nanometer wavelength light. The aforementioned expediency is due to the commercial availability of lactase as a tablet. This can be ground up and extracted with phosphate buffered saline by having the suspension liquid vortexed and centrifuged to isolate the supernatant lactase extract. Using phosphate buffered saline as a buffer, we can observe the reactions between the extract lactase and the substrate ONPG and mark the rate of reaction in test tubes incubated at 37 degrees Celsius dry baths at 30, 60, 90, and 120 seconds by use of a stop solution, sodium carbonate, increasing the pH until the enzyme is denatured. For redundancy purposes, there are 3 tubes per time mark. Control tubes are also set up for the enzyme as well as the substrate separately. Any returned values from the control tubes should be added together and subtracted as a background measure to reduce error. In order to replicate this experiment, you will need lactase tablets, a mortar and pestle, 1 milliliter of ONPG, 20 milliliters of PBS solution, 6 milliliters of sodium carbonate, pipettes and tips, applicable centrifuge and vortex, dry baths set at 37 degrees, microplate reader, and 96 well plate. We can see from the results of this rate of reaction is very linear. Approximately every 30 seconds, the absorbance rises by 0.1 within the bounds of the experiment. Since, according to the Beer's-Lambert law, absorbance of a substance increases linearly along with the concentration, we can conclude that there was a steady increase in orthonitrophenol. the real-world connection. Speaking of lactose, there is a sizable portion of the population that do not have/produce enough lactase in order to break down the disaccharide. Enzymes are required for the body to break down disaccharides like lactose since they can be too large, while monosaccharides are easier to deal with. But since a lot of people lose their ability to produce lactase after their infantile years, where their diet is much more dependent on milk, they can't drink milk in their adult years without getting sick or becoming flatulent. Remember I mentioned the availability of lactase as a tablet? This is so that people can consume lactase tablets and be able to consume dairy products without having to suffer the side effects of lactose intolerance. Thank you for watching.